Hi, and welcome back to Codex. Our speaker today is Professor Sylvester Eriksson-Bique from the University of Jyväskylä. Dr. Eriksson-Bique is an expert in analysis on metric spaces. Today, he will tell us about BiLipschitz Embeddings. Please take it away, Sylvester.
Thank you. Thank you for the invitation. It's very fun to give this talk for two reasons. It's to a completely new community. So thank you, Joey, for finding my work and for inviting me to tell about it. And the other reason is I really like to give this talk is I haven't talked for a while about this specific work. This was my thesis work that I did as a PhD about 9 or so years ago. But so it's a lot of fun to get to talk about this, and especially to the new audience. And I realized that this might be a bit of an outlier in the seminar. So I come very much from pure math, from geometry and analysis. So if I go too fast or if I don't explain something, etc., please do let me know. I'm happy to try to explain things in as much detail as possible and in a not technical manner as possible. But without further ado, the main object here is BiLipschitz embeddings, so mappings from a space X into usually Euclidean space. I will say maybe a few things about other spaces, which distort distances by at most some factor. So the upper bound here, talking about the Lipschitz bound, and then you also have a lower bound. So you insist that to be uniformly throughout the space for all x and y in the space. Now, one example that I like is that of an ellipsoid given by this equation. So what this looks like is that you are in R3 and you have in the xy plane, you have the unit circle. And then above and below it, you have two caps of height, or thickness here is roughly, or is 2 over n from the north to the south pole in this case. Now, this space, if you think of it as a subset of R3, then it's isometrically embedded into R3. So there's nothing very interesting. But if you think of it with the Riemannian metric that is induced by the embedding into R3, so the induced metric or the intrinsic metric, then this embedding, it's still isometric in the Riemannian sense. So if you look infinitesimally at the space, lengths are not distorted, but lengths are distorted if you take points that are far away. So if you take, for example, the north and south pole, there's distance in Euclidean space is 2 over n, but on the space, the distance is roughly 2, because you have to go to the equator and you have to go on the other side. So this is an example of how isometric embeddings, as you might have heard of Nash's theorem, are different from BiLipschitz embeddings. So here's a subset that is a Riemannian isometrically a subset of R3, but it's not BiLipschitz directly. But there's a simple way of embedding this BiLipschitzly, and I don't want to draw a formula, but you can just imagine that you keep the equator fixed, but then you just poof up the north and south hemispheres to the unit sphere. Just stretch them in some nice way. And you can make this in a Lipschitz and BiLipschitz fashion. That resolves this issue about the north and south pole being close. Other examples, if you prefer one-dimensional examples, are if you have a circle S1. The circle S1 has many isometric embeddings in the plane. Here's example of one of them, or maybe with, like that. This, any kind of curve of the same length is an isometric embedding, but these are not BiLipschitz, or are BiLipschitz only with a very bad constant L if the points are being pushed together like this. So part of this is giving a BiLipschitz embedding, and another part actually is controlling this constant L. So usually if you have a compact metric space, say, then you always have some BiLipschitz embedding, often, but we want to also control the L in terms of some natural parameters. So not just existence, but quantitative aspects. So there's a small thing about normalization just to fix things. Because I can scale the function f, you can always divide by L so that this upper bound is 1, and then you have a lower bound that is b. And this b here is called the distortion of f, or the optimal b, the best b that you can place in this inequality is the distortion of f. And if we vary over all such functions and all dimensions, including infinite dimensions, so L2 spaces, infinite Hilbert space, which is thought of here as the infinite dimensional Euclidean space, then the best constant, the infimum over all such distortions of f, say now I'll write this to this Hilbert space, and this is called C2 of x. It describes how well the space sits inside the Euclidean space. And there are very simple examples of how metric spaces may not sit inside Euclidean space. And one nice example is this triangle where the length of the edges is all 2, and then you add 1 point here where the distance is exactly 1. So 3 black points you can map isometrically to Euclidean space, any equilateral triangle of size length 2. But where does the center red point go? It is trying to sit on all of the midpoints of all of these 3 edges at the same time, but it can't. So it has to make some choices, and all of those choices incur some distortion. So that's a simple example of a phenomenon. You actually will see this kind of a thing, that having midpoints is something that makes BiLipschitz embeddings a bit difficult, or that sometimes force distortion. So yeah, now some examples, and I chose just 2 examples to exhibit some of the methodology of how you find these BiLipschitz embeddings f. So a very classical result is the Kuratowski embedding result, which is, I'll just say, in the finite metric space case. And a lot of that we could say, if we were just interested in data, just focus on finite dimensional space, finite element spaces. There we can embed every metric space x of n elements into an n-dimensional L infinity space. So this is just R to the n with the supremum norm, or maximum of the coordinates. And what you do is you take x and you map it to the distance vector dx x1 and dx xn, where x1 through xn are the enumeration of the elements of x. And this is an isometric embedding, in fact. Isometric in that they preserve distance, or one BiLipschitz embedding. Now, if you want, so this is L infinity, if you want to go to Euclidean space this way, you can take the identity map to Euclidean space, but then you incur square root of n distortion with this method. But still, it is a way to embed a finite metric space into Euclidean space. And why I mention this is that in a certain definite sense that hopefully becomes clear later with examples, in my methodology, or how I and many of my colleagues, how we construct BiLipschitz embeddings is essentially just distance embeddings. We don't do anything super much fancier than that. So in a way, this Kuratowski embedding, even though it seems so simple, is actually a prototype of a very broad class of constructing embeddings. So yeah, Now there are other methods, and I was actually, in preparing for this talk, I was looking at this work by Joey and Dustin, and I guess Cahill is not here. So I was looking at your work, and there I noticed that you constructed embeddings of similar object that we'll soon see, of quotients of Euclidean space. Here G is some subgroup of the isometry group of RON. We'll define this in a bit more. But there you don't look at distance embeddings, but you look at some homogenized versions of polynomial embeddings. So you have some polynomials that are symmetric with respect to the action of the group G. But then you have to, so this would be actually the embedding on S n-1, so the unit sphere to Rn, and from this you can then construct embeddings of the whole space. So just to simplify what I got very quickly, the paper has a lot of other, a lot of interesting ideas there. So that's one of the differences in these approaches, is that we really focus on these distance embeddings, mostly because they're versatile, they apply very generally, they're simple to get a handle on, simple to analyze. But there are also other methods, such as these polynomial embeddings. I know that some people embed using harmonic functions or heat kernels, I've heard of before. So there are also other ways of building embeddings, but this is the way that I focus on. Okay. So some good news and bad news about this. So every metric space, so whether it's finite or not, embeds into L infinity. We saw that came from this distance embedding. If it's infinite, then you have to have infinity coordinates. I should say separable here, if I want to embed it to L infinity of n. So there are many spaces with embeddings, but L infinity is not our desired target. Our desired target is Euclidean space or Hilbert space. So there is another theorem that works very generally. It's called Aswad's theorem, that says that if X is metric doubling, and I'll define what this means. This means that for every X in your space X, for every R positive, there exists X1 through Xn, such that Bx capital R is a subset of these n balls with centers at xi and radius half the radius. And this n has to be uniform. So there exists an n such that this is the case. As a picture, you have a ball of radius r, and you can fit at most finitely many balls of half the radius. Inside there. Okay. This is a Euclidean space is R over 2. Euclidean space is doubling. And it turns out that if you BiLipschitz embedding into something, it's a small, nice exercise in this property, if you haven't seen it before, that it remains invariant. So the previous space, subspaces of a space with are doubling, and then pre-images or BiLipschitz maps leave this property invariant, because the ball, it just inflates the radius by a factor. So this is a necessary condition for Euclidean embeddability. You can think of it as a finite dimensionality condition, because the number of these balls is roughly exponential in the dimension. So the logarithm of this quantity is some measurement of the dimension, a doubling dimension, sometimes called. So you have to be doubling in order to embed, and the question is that enough? Well, it's almost, Aswad says it's almost enough. That if you change the metric by something that somewhat seems like a small change. You raise it to a power, and this just means that you take the distance and you literally just raise it to a power alpha, because power alpha is a concave function. When alpha is between 0 and 1, then the triangle inequality is preserved, and this is a new metric on this space. Whether this changes a lot or not, it depends a little bit what your interests are and what the problem is, but this deformed space can BiLipschitz embed. And I won't say much about this proof. I won't say much about this proof at all, but I will hint at the fact that there is actually a connection between 1 and 2, because the proof of Aswad embedding, what it kind of looks like is that you have a mapping that consists of many components, and it's a bit easier to think of having Hilbert space, so infinitely many components. And what each of these things look like, these are Kuratowski embeddings, some type of Kuratowski embeddings. So they're distance embeddings at scale, at dyadic scales. So F1 takes care of the points that are roughly at distance 1, F2 takes care of points that are roughly at a distance 1/2, F3 takes care of points that are roughly at a distance 2 to the minus 3, etc. And where this alpha, what it plays a crucial role is that you have infinitely many components or infinitely many scales on which you have to do things. By snowflaking power, by a power alpha, you make a certain sum that appears in this argument converge geometrically, and that guarantees you an upper Lipschitz bound. The lower Lipschitz bound actually is a lot easier because it's enough to look at one of these components. But when alpha is equal to 1, this fails entirely, because you get all these interactions. You get infinitely many interactive terms, all of them roughly of the same size, and they just produce infinite, basically, infinity. So what I'm saying, you can prove these very general results about metric spaces, Aswad and Kuratowski, just by looking at distance embeddings and slightly modifying them and doing some normal grouping and other techniques. Okay, so some good news. You could go a little bit further. Actually, so I also had some work about trees, what we call bounded turning trees, but I won't define here. If somebody wants to know, they can look. But in these cases, you can construct embeddings using the very simple geometry of the space. Basically, to embed at the next scale, you just have to add some hairs or some pieces to your space. And you can think of this on the domain side, or you think of it in the Euclidean side about how you glue new pieces to your image side and then guarantee that these things are BiLipschitz. So in the geodesic space, this was done by Kraftgamer, Gupta, Talwar, and Matuszek had some crucial results. And then we had a more general version in non-geodesic trees, but that are still bounded turning, with Geisy David and Viron Bellis. And the same idea, really, you look at different scales, you use distance embeddings or distance-like embeddings, and then you just combine them and see whether you get these interaction terms or not. And due to the simple geometry and topology of a tree, you can avoid those interaction terms. So you can go a bit beyond. And you can also get better embeddings. They are also built using distance embeddings. So in the finite case, so Bourgain's theorem says that if you have an n-point metric space, then you can embed it always with something that is big O of log n distortion. So the Kuratowski argument of going to L infinity and then to Rn had distortion square root of n. But here you can get actually a lot less than that. Bourgain's argument still very much uses distance embeddings, but the way he chooses the distance embeddings is the clever part. So his original proof was randomized, but there are later and many other proofs of this fact. It's actually a very nice paper, so if anybody's interested, I highly recommend it. But so bad news then. There's nothing better than Bourgain. So there are examples of finite metric spaces. They're not even so complicated. I mean, some very bad examples are the Hamming cube with the just the Hamming distance on it. There you get distortion as n goes off to infinity. These become harder and harder to embed into Euclidean space. These are actually not quite the examples I'm alluding here. The Hamming cube has square root log n distortion, but some other versions have higher distortion. So Bourgain is really the best you can do. The distortion has to grow with dimension, with the size of the set, if you have finite sets. And not only that, but even if you are doubling, so then Aswad is sharp, that you cannot always embed BiLipschitzly a non-doubling, a doubling metric space. So the snowflaking is really crucial, and it's not just an artifact of the proof. And this is a big topic where there's a lot of work on these types of questions, but I will say that what kind of arguments play a crucial in what these spaces look like. These look like, the most famous one is a so-called Loxo diamond. And the Loxo diamond you can construct in the following fractal way. You start from the unit interval, 0, 1. And I think of this as a graph with 2 vertices and 1 edge. Then you replace the edge by the following gadget. And this is a new graph where the edge lengths are now 1/4. And why I do that is that I preserve the distances between the endpoints here. Then every edge is again replaced by this gadget. I won't draw the whole thing, just some parts of it. And now the edge length is 1/16. And you do this infinitely often. Or you can do it finitely many times as well. You get a sequence of spaces xn. And you can show that it becomes more and more difficult to embed these spaces. Actually, no, sorry, square root n. Yeah. You can also use this to prove that is sharp, but well, with the square root, if you're happy with the square root. And why is this difficult to embed? There's a funny thing that happens here, that you have a line segment that is a geodesic. You should think of it as a rope that is taut, that is not loose at all. And it gets copied into 2 geodesics. And then that same geodesic gets copied even more. You get this whole family of geodesics, and you can check that the construction of the metric is such that each one of these paths, that monotone goes left to right, is in fact a geodesic. So you have these infinitely many, actually in the limit space, there are uncountably many geodesics that connect these 2 endpoints. Now, what happens to their image? You can imagine these are ropes, infinitely many ropes that are tight. Now you're mapping them to Euclidean space. But what you have to do, each of these ropes is trying to remain tight, but you have to pull them apart. Why? Because the center points of these geodesics are far apart. And whenever you pull them apart, that incurs distortion. First, at the first scale, it incurs a bit of distortion. And that causes x1 to not isometrically sit inside Euclidean space. But then at the next scale, x2, you have to pull apart even more. And that causes an increase in distortion. And you can show that this increase actually accumulates and goes off to infinity. This is the proof that locks a gate for this fact. So it's these facts that you have geodesics and many midpoints that are far apart. So if we go back to this picture, it's the same mechanism that prevents embeddings here, having many midpoints as here. And that's one of the features that really causes problems. And actually, Aswan embedding, what makes it possible is that you don't have midpoints. So snowflake spaces do not have midpoints. Even more bad news, you can construct these spaces as manifolds. So you can take this space and you can thicken it into a little tube and make this into a manifold. You can make and you can even sort of make this go off to infinity and construct as manifold that contains within it arbitrarily bad spaces. Any graph, finite graph that you want. So even a manifold isometrically embeds an Euclidean space, but does not BiLipschitz embed necessarily. You have to make it non-compact, and you have to make the curvature non-zero. So there was some hope that you could say something more about flat spaces, but unfortunately, not even there. So there exists flat tori donuts that are arbitrarily difficult to embed as the dimension increases. So Cott and Nauer observed this, that the distortion grows as square root of n. And later, Agarwal, Regev, and Tian gave a so far best result that you can always find some embedding with square root n log n. So there's a small gap here that somebody should fill out to figure out whether that log n is necessary. There was an earlier result that was n square root log n, but they improved that. So we'll talk soon about tori more, maybe give a sense. But so what did I show along this line of work then? So I looked at quotients of Euclidean space, where G is a discrete group of isometries. So G is again some subgroup of the isometry group, and isometry group of Euclidean space. So you don't just have rotations, but you also have translations. So it's really the semi-direct product of Rn and the orthogonal group. And being a discrete, that just means that if you fix any point x, the orbit of it doesn't have accumulation points. So the orbit looks like some kind of lattice, really, in space. Now, if the orbits are discrete, then we can properly define a distance, which is always positive. That follows from the discreteness. In this case, that the distance between two orbits, or equivalence classes here, we say x is equivalent to y if there exists a group element such that gx is equal to y. So if they lie in the same orbit, then we take the distance between those two orbits as sets, which in the group case just can be measured in this way. So these quotients, they can have some singularities if the group G has fixed points, or if the group G is acting freely, that is without fixed points, these are actually manifolds. And they are locally look like Euclidean space. So they are flat spaces. They have a metric that is locally flat. So there's no artifacts coming from curvature. So, and what I showed is that there always exists a BiLipschitz embedding of this space into some high dimensional Euclidean space, and the distortion depends only on n. So it's uniform for a given fixed n. There were other cases I studied as well. I studied some small curvature manifolds, so the manifold had bounded curvature. And then later, Zolotov gave a very different argument that also proves my theorem. He talked about SRA free spaces and bounded dimensional Alexandrov spaces. But I won't say things about those due to lack of time, but what I will just say is that actually the techniques here are somewhat similar, or the building blocks are the somewhat similar as in my theorem. So the basic scheme is the same, but Zolotov had a brilliant idea that you actually don't have to do, you can do these arguments more generally. And what he needed was this kind of an SRE free space that really is a codification of saying that distance embeddings work. So this was the main result. Now, some things I want to say about this theorem and how it relates to, say, this work by Cahill, Iverin, and Mixon. So in their setting, one big thing is this group G. So for them, and what I was almost making a mistake there later, is that G is subset of the orthogonal group. So this always fixes the origin. In my case, I was interested primarily, well, those cases as well, but more generally groups that don't fix the origin. So they might have some translational part. So that's one major difference. The other major difference is that actually here, Kyle, Iver, and Mixon also considered quotients of Hilbert space. And there you have to be a bit careful because these orbits often are not closed. So it's much more restrictive to say that you have a discrete group. Finally, another difference is that they don't assume anything about discreteness. So for me, discreteness is somewhat crucial, at least for the methods that I use. Well, maybe in the questions I might have time to say something about that. The claim is true without discreteness. Then it would follow easiest, I think, is through Zolotov's work, because these quotients are always Alexander spaces, even if the group is not discrete. But my techniques really used quite heavily discreteness. There are some special results that hold for discrete groups. So, but okay. In the remaining time, I want to really focus on some examples in the building blocks, because I think these were actually what motivated me, that gave me a sense of how to work these out. And the first thing is what a flat tori. And this is actually a bad bound. This is not much worse than Oded Regev and et al. Did, but it proves the uniform bound in the dimension. So what is a torus? A torus is Rn quotiented by a lattice lambda. So lambda is a discrete group of translations. So it is just a subset of Rn that is discrete. So it's something that's spanned by n vectors with integer multiplication. Okay, so there's a very simple lattice that we all know. So if lambda is just the integer lattice, then Rn quotiented by Zn is nothing other than the product of R quotiented by Z. And this is nothing but S1 times S1. So S1, we can choose a nice embedding into R2. So we can embed every one of these S1s into a separate factor of S1. So we can embed this into R2 to the power n, at least. You can even do this polynomial. This is a polynomial. Well, not polynomial. It uses sine and cosine. But you can write it out. Okay. But this might, at least it was a bit difficult for me initially, but not all tori they are topologically the same, S1 times S1 times S1, but there are very different lattices. So already in 2 dimensions, a lattice is generated by 2 vectors if you take the hexagonal lattice, for example, then where the angle is 60 degrees, then it doesn't split as a product. There's some angle between them. And if you go to a 3rd dimension, this phenomenon gets even worse. You get vectors that are very close to the hyperplane spanned by the first 2 vectors. And then further and further. So you don't get a uniform bound between the angles of these spaces. So if you just choose an arbitrary basis v1, vn, and do this kind of an argument of splitting it, then you get a very, very bad bound. But there is an algorithm that comes from lattice algorithms that you can choose a good basis. And you choose this basis by v1 is the shortest element, v2 is the shortest element in lambda, take away the span of v1, in the integer span of v1, etc. And then you choose a linear map that maps the v1, vn to the standard basis. If you choose an arbitrary basis, then this might not be BiLipschitz, but when you choose a short good basis, then this, and you have to actually change this a little bit because of the lengths of the vectors. You have to use the lengths of the vectors in your basis. You can make this BiLipschitz with a constant that only depends on n. The BiLipschitz constant here depends on the angles between these vectors. And there's a standard lattice results that give you this. So once you do that, you've converted your vector into orthogonal, and then you can use one. So you realize that this space is BiLipschitz to a product space. But some of these circles might be very short, because some of the vectors in your basis might be very short. So something like this. Imagine a torus built by one side being very short and the other one being very long. Great. So a lattice, we can always make a product of something very simple. And there's a trick that plays a role in the argument, is choosing a good basis. So the building block for these embeddings then is that we take embeddings for these factors and we combine them together. So we can tensorize embeddings. If you have embedding of x, of y, you can get an embedding of the product space. A very simple procedure, but the second one is a bit more complex, is that of a holonomy bundle. That sounds fancy and weird, but what it is R3 quotiented by this action of Z3. And what I want to think about is that I have a circle where these points are identified. And then perpendicular to it, I have a copy of R2. And as I go around horizontally, this copy gets rotated. And it gets rotated by an angle theta. So when I go back here, this point gets identified with the point with the rotation. So you can write this using complex notation like this, that you have an action of z which translates the first component, and then the second two components that are complex numbers are rotated by an angle theta. So this is a very common phenomenon in discrete groups in R3, that you get this kind of pieces. So here, what we have is the zero section of this thing. This is a vector bundle, actually. The zero section of here has a BiLipschitz embedding. So this is just S1. So we know an embedding for that. Let's call that Z. And what we can then do, what our arguments are based on, is that we can look at points that are at distance roughly 2 to the k from that center fiber. And what these look like when k is bigger, let's say when k is very big. So if we look at points that are at distance 2 to the k, well, what we get here, we have a circle, and the circle is glued to itself with a rotation. But what is that? That's topologically a torus. Not just topologically, but metrically. It's isometrically to a torus. So that BiLipschitz to a torus. So at the distance k, we have a torus, but we already know how to embed tori. This theta factor here tells us what type of a torus that we get. So we can embed the zero section, and we can embed these different length scales, roughly 2 to the k, because what they look like is this section where the distance is constant, which is a torus, and then a factor of r locally. So they look like a torus times r, and we know how to embed those. So here there is a technique called decomposition, that if you can embed some part of the space z, and then at a distance r, you can embed a theta times r ball. If you can embed all of these things together, you can put these in an organized way with the assumption of doubling to get a BiLipschitz embedding of the host piece. Sort of like a puzzle piece where you're putting the pieces together, and you put them in different coordinates. But this is a general principle, but it's just a general argument. But with this, you can decompose this problem of embedding this into embedding simpler things. And I will say a little bit about the general case. Just I'll say one picture that I very much liked, at the expense of maybe going 1 minute over time. That of a lens space. So what is the lens space? It's given we have we represent the unit sphere as 2 pairs of 2 complex numbers whose lengths sum up to 1. And then if we wanted to represent c times c, we can add a factor of the module. Yeah, then we just take all pairs of complex numbers. But here we're restricted z squared plus w squared equals 1. But this space, if you can visualize it, because this is the stereographic projection of the 3-dimensional sphere is the 3-dimensional space, and z equals 1 is the z-axis in this stereographic projection, and w equals 1 is a circle around it. This is these are the fibers of the Hopf vibration, two of the singular fibers of the Hopf vibration. And what is happening here is that what this group action is doing, this is a group action of zp, so z quotiented by p times z, and p is an integer. What it's doing, it's rotating the first factor by a certain amount, so it's moving a point along here. But it's simultaneously moving a point along the other circle, but a different amount, different power. So if you look locally close to this, some tube around this first point, circle, some normal neighborhood of it, what is happening is that you are identifying 2 copies of this circle, but with a twist. So the normal bundles of these is actually you're identifying with a twist, with a certain angle. And why I want you to see that, and that's the only part I want you to see, is because that's exactly what this is. Locally, these are 2 things are the same thing. BiLipschitz. Topologically, they're locally homomorphic, and metrically, you can show that these metrics are almost the same to a factor. So in a neighborhood of these 2 circles, you are actually a holonomy bundle. And so if we know how to embed holonomy bundles, we know how to embed the lens space, because we decompose it into these 2 neighborhoods. You can make these overlap like the north and south hemispheres and embed both of them. So these are really all the pieces that there are. You have to embed a torus, you have to embed these holonomy bundles, and then you have to be able to put these pieces together. But the general argument is basically the scheme is this. You start from a given space. You have some numbers that describe its complexity. If there are questions, I can say more about that. But and you show that spaces that are very simple, that have complexity and 0, they embed. And then you have operations that decompose the space into simpler ones. So there's a lower dimensional part in the space. You already embedded all the lower dimensional parts by induction. And then outside of this lower dimensional set, you prove that in these theta R balls, you actually have lower complexity. And the whole thing, the tricky part is getting this all quantitative and not just quantitative and with constants that only depend on the dimension. But I'm already 3 minutes over time, so thank you for your attention.
But you have more time. Sorry, I'm losing my voice. You have more time if you'd like. In fact, you have at least 2 minutes left, but we started a little bit late. So I think if you have at least 5 minutes, if you want them, if you want to be
I could, well, yeah. Well, I could say something, maybe one thing more than for those interested and still with me. So, I mean, something that specifically, or I don't expect that people maybe fully grasp this idea, but that these embeddings are really kind of distance embeddings at different scales, and you're doing an induction where you're simplifying the space. So you're decomposing it into pieces that are simpler, and then you have one embedding that takes care of the macro structure, and then by induction you can take care of those smaller structures. And that can be articulated with such a local to global lemma. I mean, we don't actually use this in the paper, but this is a good organizing principle. That if you have some space that you're trying to embed, and you can embed, you prove that for every x you have some radius that you can embed. Then what you can do is you cover the space by these balls, and they're balls, they have centers in n. And then this kind of problem, it decomposes the problem into two things. One, embedding these balls, and two, embedding this macro structure. So in the math, what really makes these proofs works is that the smaller scales are simpler, and the macro structure is actually very simple. It's something like R or a product space, etc. That's one thing. And the other thing is I could say something about this discreteness. Why is it relevant that I worked with discrete groups? Well, there's a very beautiful theorem. It's used in, I'm sure, crystallography, lattice theory, etc. That one can classify fully, well, describe fully all discrete groups of isometries of Rn. And the description is not super, it looks maybe a bit complicated at first, but it's kind of, once you stare at it for a long time and think what it's really meaning, it's not so difficult. So one part of it is that every group, it has a normal subgroup, which is translational. Lambda, which acts by translations on some k-dimensional subspace. So there's a k-dimensional subspace, and you have a lattice in there. So when you have a k-dimensional subset and a lattice, you should think that you have a torus. So inside any group quotient, there sits a torus. It can be a Klein bottle if it's not orientable, but yeah. So, and then there's all the rest of the group. There's a finite group H, and that finite group, well, it can cause things like the Klein bottle, the disorientability, but mainly what it causes is that in the normal bundle here, where we have n minus k dimensions, the just normal subspaces, these get twisted as we go around. And there can be complicated group actions in that H. But H leaves this z-dimensional subspace invariant and rotates this n minus k dimensional subspace. And it can be any finite group, almost any finite group. So there's not much you can say. Of course, G itself could be a finite group, and you could have had an isometric representation of a group. So this is really what the basic building block of our induction, because here we have the torus that's lower dimensional, and then we have a fibration of it. So it's some sort of holonomy bundle. So that's maybe, yeah, that's now my time is up. So yeah.
Okay, thanks a lot, Sylvester. Let's all thank our speaker by clicking a button with a smiley face and a plus. I'm going to click the clap one. All right, and I think we can stop the recording now.